A long time ago, life used to be much simpler. In your first contact with counting, balancing numbers was never a problem. Look here at these scales. If you need an unknown number to represent the number of apples, the answer is obviously 3. If I try another case here for something to represent yay number of oranges, it's obviously 5. And if I were to combine these two fruits, it's clear that apples and oranges are two distinct items, which means that I will still have 3 apples and 5 oranges despite them being put together. Wasn't that easy? Hang on, I'm barely getting started here. Life got tougher ever since algebra came into the picture. But what you should know is that it simply replaced the pictures you were so familiar with. Want to count the number of x and y's? They are still uniquely different, and this example still represents 3x plus 5y. And this is where math deviates into numbers again in the form of surds. As counting and representation becomes more complex, there is a need to hold on to neat packets of numbers in their square root forms. These bundles can then be manipulated easily like so. Tapping on skills like prime factorizing and the recognition of perfect squares, a number as large as the square root of 162 can be decomposed into 2 times 81. Since the square root of 81 is 9, while the square root of 2 cannot be simplified further, a simpler representation would be 9 square root 2. And with that knowledge, apples and oranges take on the form of algebra, surds, and numbers. Need to find x and y in this case? To balance an equation, first represent your unknowns with x and y. Observe that these unknowns are unique. One has a coefficient of 3 and the other a coefficient of 5. So, if I decompose 12 into 3 times 4, the only logical conclusion is that x equals 4 and y equals square root 7, since I have to compare the corresponding fruits. How about something harder like this? Square root 50 and square root 68 look like rather annoyingly large numbers, but prime factorization allows you to break them down into manageable forms. Observe how 50 decomposes to become 25 times 2, with the square root of 25 eventually being 5. The number 68 suffers the same fate, eventually forming 2 times square root 17. All of a sudden, life seems much simpler. Since the coefficient of x is square root 2, it has to be assigned the value of 5. And since y is attached to the number 2, it has to take on the value of square root 17. Seems like a lot? Wait a moment, there's still one more thing to talk about here. The concept of distinct entities with apples and oranges translates across other branches of math as well. It is, after all, a logical approach to compare similar terms. Indices is the study of exponents, also known as the powers of numbers, which are written as superscripts. The number 32 is due to 2 multiplied repeatedly 5 times, and hence written as 2 to the power of 5. A larger number like 125 can be prime factorized to realize that it is the number 5 multiplied by itself 3 times. And so, we use this special balancing approach when finding how many 3's and 2's are multiplied together to obtain 648. By representing unknowns as x and y, prime factorization is used repeatedly to decompose 648 until you can go no further upon achieving and there is no other logical conclusion other than x equals 4 and y equals 3. It really doesn't matter what fruits you use. Eventually, we can represent these unknowns algebraically with the assurance that A, the equation always balances, and B, prime factorization always simplifies the problem. The only base left uncompared is 2, so that has to be x. The power of 5 is by default 1, which has to be the y value. And the z value has to be 2, since they are both powers of 7. Hold up a moment here. If you haven't realized, one detail you might have overlooked is that surds are terms separated with a plus or minus sign, whereas indices are terms separated by a multiplication sign. So don't confuse the two. In conclusion, apples and oranges overly simplify the math concept of equivalence. The evolution of simple shapes and pictures to compare values progressively towards algebraic symbols as math becomes more difficult. Surds and indices emphasize the importance of such comparison skills. Appreciating how values can be compared across both sides of an equation allows for solving, grouping, and packaging of terms for more straightforward solving. And now I guess I'm really done.